Okay, Mark Wilde, polar codes.
Okay, so sorry about that. Thanks for having me at this conference. And in light of the panel discussion last night, I'm hoping the panelists won't start throwing tomatoes at me, but my talk is about codes for quantum communication, not necessarily fault tolerance. We're trying to find codes that can achieve the capacity of a quantum channel for communication. The fact that I'm so interested in this, you can partially blame on Todd Brunn. He never made me take an oath to preserve, protect, and defend the quantum computer. So in the classical world, since about 2008, there's been some work on codes called polar codes, which have pretty remarkable properties. And we've been going to these information theory conferences for the past few years, and so we decided recently it would be a good idea to see how to make these codes work in the quantum domain. In parallel, Renato Renner and his group in Zurich, it turns out that Renato Renner lives in the same apartment complex as the chief editor of the IEEE Transactions on Information Theory, and they have these birthday parties for their kids. You know, these information theory people have birthday parties. And Renato Renner asked the chief editor what he thought the biggest advance in coding theory in the past 10 years was, and the chief editor said, well, without a doubt, it would be polar codes. So their group started pursuing it, and about the same time, we had papers appear on the archive. So we did these, Saikat Guhai and I did these two papers here, and recently, one of the co-authors on that paper, Joe Renes, we put our heads together, and we came up with polar codes that can achieve this exotic superactivation effect that Graham Smith was talking about, where two zero capacity channels, you can put them together, have non-zero capacity, except this is a near-explicit code construction for doing that. Okay, so just a little motivation. From quantum Shannon theory, quantum information theory, we have a pretty good idea of capacities of channels for sending classical data or private classical data or quantum data. Only for certain channels we have this idea, but there's still some open problems. And there's been a fair amount of work on quantum turbo codes by David Poulin and others in an attempt to achieve the capacity of a quantum channel, and also quantum LDPC codes. And these are explicit constructions, but you can't actually prove that these codes are capacity achieving. And there's actually very little work on codes for sending classical or private data, even though this is an important problem where you can actually demonstrate a quantum supremacy, as was said last night. Turns out for a bosonic channel, if you have your detector perform a joint collective quantum measurement, there can be a significant increase in the amount of classical data you can send over this channel when there's a low photon number. Okay. And so, as I was saying, these polar codes are promising in the classical world, and from what I hear, they're being incorporated into standards for communication. So we thought, why not explore their quantum generalization? And the result we found is a scheme that's near explicit. There's still some work that needs to be done in this direction. We can prove that they're capacity achieving for certain channels. Okay, so I'll start by describing this channel polarization phenomenon. And we'll do it for the quantum case. And in particular, I realize this is not a CEC conference, but I'm going to start out with the classical case to build up to the quantum case. And eventually, I'll get to QEC near in the talk. OK, so we'll begin with a channel that is a classical quantum channel, a CQ channel. I'll call it W. It has a classical binary input X. And conditional on that, some state rho x is prepared at the output. And it doesn't matter the dimension of the state. Okay, so if you put in 0, out comes rho 0. Put in 1, out comes rho 1. And an important channel parameter is something I'll call the information of W. In more detail, we'll call it the symmetric Holevo information. And it's just the mutual information, the correlations you can establish between the input and the output when you select the input uniformly at random. Okay, so that's why it's called symmetric Holevo information. If you have a formula, it'll work out to this. And you know, I could evaluate this information quantity with respect to this classical quantum state, which corresponds to an ensemble I could prepare using this channel at the output. Okay? And just to give you some idea, this parameter is equal to 1 if the channel is perfect. and it's 0 if the channel is totally useless. So the useless case is when the cable is cut, like when Graham Smith was saying in his talk. Okay, so this is an important channel parameter. And the inventor of polar codes is a professor named Arikhan, and his idea was to take 2 copies of this channel and just do a classical C0, okay, at the input. And what you can observe is this information preservation condition, okay? So if I compute twice the information of the original channel, it'll be this quantity when you work it out. And this is an information evaluated with respect to these 2 inputs. And since this gate is reversible, the information here is equal to the information of these when these 2 inputs are input. But what we can use is something that's well known in information theory. It's the chain rule for mutual information to break this information term into 2 parts. Okay, and this is very important for the polar coding idea. Okay, and this chain rule, it's suggesting that we can actually think about 2 different channels. There's a channel from the bit U1 to the 2 outputs, and a different channel from the bit U2 to the 2 outputs with the bit U1 as side information. Okay? So to give a picture of this, this first channel is a bit channel from U1 to the 2 outputs where this input is acting as noise. It's not known to the receiver. Okay? And I'll call that W minus. You'd maybe think it'd be a worse channel than the other one where U1 is available as side information, right? So I'm just taking this. This channel here is a bit channel from U2 to these outputs, U1 and the 2 quantum outputs. And what's happening is that this U1 is available as side information. Okay, so when you look at these pictures, maybe it's already hinting at how a decoder could work in decoding these bits. Okay, and what we came up with is an extension of Arikhan's ideas. We call it a quantum successive cancellation decoder. Okay, that's a name that comes from information theory, but the idea is that the decoder would first decode U1, assuming this is noise, and the receiver would do this by doing a simple quantum hypothesis test, right? Conditional on U1, there's some state that's prepared at the output. I could call it, say, 0 or sigma 1, and the receiver would just do what's called a Hellstrom measurement, project onto the positive eigenspace of the difference of these 2 operators that are prepared at the output, okay? And then, assuming that the decoder corrected U1, that the decoder decoded U1 correctly, it's then available as side information to do a second quantum hypothesis test to determine U2, okay? So that's the idea behind the decoder. But what you do is you continue this construction recursively, okay? Because we're going to need many copies of the channel to make some interesting statements. Okay, so what I'm doing here is I had this channel, W2, right, this block here, and I take copies of it in this recursive construction, right, so I'm placing them here and here. This operation, which it just places all of the odd indices, U1 and U3 first, it's putting them here, and it's taking the even indices and putting them next. So in this case, it just amounts to a swap of the middle 2 bits. And then I do a C0 on every pair of bits coming at the input. Okay, so the idea is just a bunch of C0s, swap things around, C0s, swap things around, and it happens recursively, and it builds it up. Okay? And you can use the same idea of the chain rule, this information preserving condition, 4 times the original information of the channel. Using the chain rule, we'll distribute in this way, such that I can think of 4 different channels now. The channel where the receiver is trying to get U1 first, conditional on that, getting U2, and so on and so forth. So a picture of that again, just to hammer that point home. The decoder is trying to get U1. These bits are random. Assuming it gets this correctly, he's U2, and these are random. So on and so forth, it continues, right? So finally we have this picture here. Okay, so you continue this construction recursively many times, and the chain rule recursively will be this, just where you're trying to get the bit I conditioned on the previous I bits, or the previous I minus 1 bits. And this is the important statement of channel polarization. Okay, so we're thinking about these induced channels from bit I to the channel outputs, right? And the statement of channel polarization is that a fraction of the channels will be completely perfect. Okay, you can prove this. And the complementary fraction will be totally useless. Okay? And the fraction of channels that are perfect is equal to the capacity of the original channel, and the fraction of channels that are imperfect, the complementary number. Okay? So you can prove this result using martingale theory. That's what Arikhan did. And we used quantum generalizations of Arikhan's inequalities to prove this result. Okay? So I'll go into that in a little detail to give you some idea of how it works. There's a different parameter we can think about that we'll call the fidelity of the two output states. Now, keep in mind, we're not considering quantum communication here. We're considering classical communication, so the interpretation of fidelity is a little different. We interpret it as a distinguishability measure. Okay, so how well can I distinguish row 0 from row 1? And quantumly, we know it's this Hilbert-Schmidt norm of these two states. And so the fidelity actually is 0 if the states are orthogonal, if they're perfectly distinguishable by some measurement, and it's equal to 1 if the states are completely indistinguishable. Okay, so since it's classical transmission, it's a different interpretation. Okay, and this generalizes the classical fidelity, which in the classical world they call it the Bhattacharya parameter. Okay, and sort of an operational interpretation of this quantity, this is a parameter of the channel, the CQ channel. If I'm trying to do a quantum hypothesis test to distinguish the bits from each other, then the fidelity serves as an upper bound on this error probability. And we use this in the proof to show that the scheme works well. Okay, so you would expect these parameters to be related, right? In particular, if the channel is good for sending classical data, you'd expect the states to be distinguishable, right? So if the channel, if the information is 1, if the channel is perfect, the state should be totally distinguishable. And if the information is 0, if the channel is useless, you'd expect the states to be completely indistinguishable. Okay? And you can make this precise with these bounds here, right? So if the fidelity is 0, this term here will lower bound the information, which then you can show is 1. And if the fidelity is 1, if the states are not distinguishable, then the information will be 0. Okay? So we can prove these bounds using prior results of Holevo and some recent results of Roga and others. Okay, and what's nice about this is you can prove things about fidelity, and that'll imply similar things about the information quantity by these bounds. Okay, so recall this recursive channel construction that we had before. We do this many times. And I'm going to call the channel induced from the ith bit, so say I is 2, we'd be thinking about U2, in the nth recursion level, so here the recursion level is 2. There's some bit channel there. And what you can show in this recursive construction is that the information of the ith bit there in the next iteration of the recursion will spread away from the middle. Okay? So there will be 2 places in the circuit that will sort of spring forth from the ith bit channel. And what happens is they move away from the center in this construction. Okay, so this is actually how the polarization effect takes hold. These information quantities are moving away from the middle of the interval between 0 and 1, and they're being pushed towards an extreme, towards 0 or 1. Okay, so that's what this is showing, and a complementary sequence set of inequalities holds for the fidelity parameter. Okay, and there's some other inequalities that you need to show this, but this is the basic idea. Okay. And we can prove the generalizations of Arikhan's ideas. Okay, so then we're thinking of this splitting process, the way that the channels get created under this recursive encoding. And you can actually model the channel splitting process as a random birth process. Okay, so I take the ith bit in the nth recursion level, and I represent it as a binary sequence. and this tells you where I'm going in this tree, right? So I modeled this as a random process, and what you can show is the fidelity of the ith channel, where I is a random parameter, right? It's this binary sequence. This process is a martingale, and you can use martingale convergence results and the inequalities on the previous slides to show that this random variable will converge to a 0, 1 valued random variable. So that's the polarization effect, okay? And what you can show is that the probability that this ith channel is 0, the fraction of channels good, is equal to the capacity. So that's the basic idea that we were able to show in the quantum case. Okay, so once you have this, it immediately leads to your coding scheme, right? I mean, it's pretty obvious from there. If you know which channels are the good ones, so this is sort of the existence part, right? We were using this probabilistic argument to say that this effect will take hold. So if you know which channels are the good ones, you send your information bits through those. And if you know the good ones, you'll know the bad ones, so you'll just send pre-agreed upon values for the ancilla bits through those other channels, okay? And then the decoder is just this quantum successive cancellation decoder. So you perform this sequence of conditional hypothesis tests to figure out your bit stream, okay? And the key tool that we use to analyze the error to show that the scheme is in fact capacity achieving is a recent bound of Pranav-Sen found in the context of quantum information theory. I call this bound the non-commutative union bound. I've said at a different conference, I think this bound is really important and can be used in many different contexts. It generalizes the union bound from probability theory, and this is used all the time in many probabilistic arguments. And so the reason this is like a union bound, I may actually go to the board, or it's right here real quick, just to show how it generalizes the union bound. So the union bound from probability theory, just to remind you, if I'm interested in computing the probability for a correct sequence of events, I can think about, I want the intersection of a correct sequence of events, right? So I can instead analyze the complement of that. That's what this first term here corresponds to, right? So when I do so, I apply De Morgan's law, right? And I'll get the union of the complements of the events. And then using the union bound, this is bounded by the sum of the complements of the individual events, right? So that's what this is doing, right, except with projectors. So this sequence of projectors corresponds to a correct sequence of events. And 1 minus that is the complement. And then it's upper bounded by the complement of each individual event, the complement of these projectors, with the exception that there's a 2 square root in front, and that comes from the non-commutativity. If the projectors commute, you can remove the 2 square root and you get the union bound. But if they don't, in general, you need this 2 square root. You can find counterexamples where you can demonstrate that this is needed. Okay. So the idea is we can bound each of these events, the events for the individual channels, by an exponentially decreasing term. And there's a linear number of them. So there's an exponential finding a linear term, and the exponential always wins. Okay, so that's the basic idea behind proving that this scheme achieves the capacity. Okay. Proving that it achieves the classical capacity. Okay, so now I realize that this is not the PEC conference, the conference for private classical communication. This is a step that we need to finally get to the QEC. Okay, so we have, and this is in relation to what David Cribbs was talking about, relations between sending private data and turning that into codes. So assume that we have a quantum wiretap channel. It's a classical wiretap channel. There's some classical binary input. It leads to a state at the output that's shared between Bob and Eve, right? So we can think about the channel to Bob just by tracing over Eve, and we can think about the channel to Eve just by tracing over Bob. So I'm going to call the channel to Bob W, and the one to Eve W star. And what's known is that if the channel is degradable, meaning that Bob can simulate Eve by applying some channel to his output, so in a sense his output is not as noisy as Eve's, then you can prove that the private capacity is equal to this information difference. So the idea is just the amount of private information you can send is just the difference between what Bob gets and what Eve gets. Okay? And so what happens in this setting, we have two different channels, right? And each are polarized in their own way. There's going to be channels that are good for Bob and bad for Bob, and ones that are good for Eve and bad for Eve. So overall, the channel will polarize in 4 different ways. Okay? There'll be those that are good for Bob and good for Eve as well. Okay? And we don't want Eve to get any information, so we won't be sending information bits through those. But since they're good for Eve, we want to randomize what she's getting. Okay? So we send random bits through those. Okay? And this all is important because it's we're going to make coherent versions of this on the forthcoming slides. Okay? Ones that are good for Bob and bad for Eve, well, that's where we can put our private data because Eve won't be able to get the information there, but Bob will. Okay? And so we just send the information bits into those. And finally, well, not finally yet, but there are ones that are bad for Bob and good for Eve. And we can't guarantee that Bob will be able to decode the bits put in there, but Eve might be able to, so we need to randomize her. So we need something that Bob will have access to such that he can decode faithfully. But we also need to randomize Eve. So the best thing we can put in there is halves of secret key bits. Okay? So don't start flinging tomatoes yet. We can show that the amount needed here, the consumption rate of secret key, goes to 0 for certain channels. Okay? And then finally, there are channels that are bad for Bob and bad for Eve. And since Eve can't get those, we'll just put the ancilla bits there that Bob knows such that it can help him decode the information bits sent through. Okay? And what we can show is if the channel is degradable such that the map to the environment is classical, so there's some density operator for Eve, row 0, row 1, and if it's diagonal in some basis, this is what I call a channel that's degradable with classical environment, then we can show that the scheme provably achieves the wiretap capacity using this successive cancellation decoder. And there are actually many channels that have this property. Amplitude damping channels, dephasing channels, cloning channels, erasure channels, etc. So this is a useful scheme. And what we can also show is that this rate of secret key required goes to 0 in the asymptotic limit. Okay, so now finally we're at the QEC slide. Okay, the basic idea is to run the wiretap code in superposition. Okay, these are ideas that were used by Devetak to prove that the coherent information is an achievable rate for quantum communication. And so what we're doing instead is using a coherent version of the same encoder. The encoder is just going to be C0 gates and swaps, right? And when you consider the channel, David Cribbs was saying any channel will have an extension to an environment as well as Bob, so the overall channel is unitary. So this induces a wiretap channel, okay? So then there will be channels that polarize in 4 different ways, just like we had for the wiretap case. Okay, so there will be channels that are good for Bob and good for Eve. Remember from before, we put random bits into those to randomize Eve. Now we're just going to put the coherent version of a random bit, which is a plus state, into those channels. There are channels that are good for Bob and bad for Eve. We put information qubits into those. There were those channels that were bad for Bob and good for Eve. So remember, they're bad for Bob, so we need something there that can help him decode. While we want to randomize Eve, we put a secret key bit there before. The current version of a secret bit is an E bit, an entangled bit, Bell states. But remember, for certain channels, we could show that this entanglement consumption rate goes to 0, okay? And then finally, there were these channels that are bad for Bob and bad for Eve. And since they're bad for Eve, we can put something that's agreed upon for Bob to help him decode, and we put ancilla qubits there. Okay. So the decoder in this case is going to consist of two steps. Remember we had a measurement, this quantum successive cancellation decoder, that worked well for getting the private information. So we're going to run a coherent version of that. Any measurement you can do sort of as a controlled operation. So we'll be doing that. And so that's the first step. Then finally the second step is a controlled decoupling unitary. It's guaranteed by Ullmann's theorem. So this part is not efficient. The first part is not either, but it's explicit, okay, and there's a linear number of quantum hypothesis tests. For Pauli channels, Renes and others were able to show that it is efficient, okay. So in analyzing the proof that this scheme achieves the capacity, we just use the fact that the decoding measurement is reliable, and also that it's secure, okay, to guarantee that the quantum data can be decoded well. Okay, so the decoding circuit would look something like this. This is the encoder consisting of all these C-naughts and permutations, and out comes something for Bob and something for Eve. This part right here, without this, is just the measurement that was this quantum successive cancellation decoder. Okay, and then running it coherently, I'm taking the outcomes and putting them in these two registers coherently. And then finally, this is the controlled decoupling unitary. Okay, so this was the first scheme that we have in this paper. Then recently, within the past 2 weeks, I've been working with Joe Renes, and we can use some of his ideas from his scheme to come up with a slightly different scheme, but there are relations between the schemes. Okay, so Joe Renes has written all these papers about how sending quantum data is like sending classical information in complementary bases. Okay, he's written like, I don't know, 10 papers on this topic. And so we're using this idea, except in this explicit context where we have this polar code construction. Okay, so the way he thinks about quantum information, I've had to learn recently, is if we have a quantum channel, we can think about a classical quantum channel where we're sending some bit into the amplitude basis, which is just the eigenbasis of the Z operator. Okay? And then if we're able to decode that successfully, coherently, we can think of the next channel in line as this phase-encoded channel where a Bell state is available at the decoder. Okay, this comes about from the decoding process. It sort of creates these Bell states that have phase information encoded onto them. So this is this phase-encoded channel. And his coding scheme is, well, channels that are good, so channels that are both good for amplitude and good for phase. There's a sense in which we'll be able to decode these channels because decoding quantum data is like decoding classical data well in complementary bases, okay? And the channels that are good for amplitude but bad for phase will need some phase bits there to help Bob decode the phase channels because those are bad in this right here, okay? And ones that are bad for both bases will need halves of E bits there because in a sense, if you have an E bit and Alice does a measurement locally in the Z eigenbasis, Bob will be able to predict the outcome of that measurement, right? And the same happens in the phase basis. If Alice does a phase measurement, if she does a measurement of the X operator locally, then Bob will be able to predict the outcome of that measurement. And related to that is why we need E-bits here, because these E-bits will help decode the channels that are bad for both bases, okay? And then finally, there are channels that are bad for the amplitude basis but good for the phase basis, and Bob will need information in the amplitude basis to help him decode these bad channels, okay? Right, so we really wanted this archive number here because it's really symmetrical and pretty, but we're gonna wait for a while to get this nice pretty number here and go for it. There's no 22222, right? I mean, so okay. So the way that this works, we have these amplitude channels, channels in the amplitude basis, And we know from the polarization results that this number of channels will be good for the amplitude basis, okay? And then from the phase results, the C system here is the half that's available to Bob for helping decoding the phase information. So we know that this number will be good, okay? And then what you can show is that the net rate, when you just consider the sizes of these sets and sort of some basic set theoretic operations on the sizes of sets, show that the net rate of quantum communication will be the sum of these two minus 1. And so we're subtracting off the EBITs that were used to communicate. Okay, what you can show, what Joe has done in previous papers, all these papers he wrote, that this rate will be equal to the coherent information. Okay? And so this is a picture I lifted from one of Joe's papers. This is how the decoder would work. First, you're decoding the amplitude information and then coherently copying it to this ancilla register. And then this process is what induces that phase channel that I had on the previous slide, where the Bell state was available with phase information encoded onto it, okay, because you're getting a coherent copy of the amplitude information in this register. Okay, so then the phase measurement run coherently acts on these two systems and copies it to this register. And finally, doing a whole linear number of controlled phase gates, you can decouple the environment. This isn't dynamical decoupling, but this is just a decoupling operation. And so using a linear number of those, you can decouple the environment and get the quantum data that Alice was trying to transmit to Bob. What's nice about this is that this is explicit, this is explicit, and this is explicit. This is a linear number of coherent quantum hypothesis tests run in succession. This is the same type of thing. So this work reduces the problem of the decoder for general channels to figuring out how to make these two things efficient. Okay, and this is known to be efficient. So this is an improvement over the previous scheme that I had with Psychot. Okay. Now, what's sort of the cool statement we can make is that this scheme will achieve superactivation for the channels that Graham Smith and John Yard gave as examples of channels that could exhibit this phenomenon. So the two channels that they gave were this four-dimensional input PPT channel, positive partial transpose channel, that has zero capacity. The other channel, by Graham's no cloning theorem argument, was an erasure channel, and it has a 50% erasure channel, and that has zero quantum capacity. Okay, so, but put together, these have non-zero capacity, and the result is a 16-dimensional channel. Okay, so we can factor these 16 dimensions as a tensor product of 4 qubit input spaces, right? And we can use this qubit polar coding scheme to achieve the coherent information. Okay, and the way this works is you coherently decode these amplitude and phase variables in this order. So first you decode the amplitude variable for the first qubit channel interfactor, and then using that as side information in this coherent decoder, you decode the second amplitude variable for the second channel in this four-fold tensor product. And you keep doing this. So after 4 rounds, you'll get all the amplitude variables. Then you can use those as side information coherently, quantum side information, to decode the phase variables. This scheme will achieve the coherent information. One thing we can't show is for these channels how to make the entanglement consumption rate go to 0. Okay, because before we needed this condition that the channels were degradable, but this doesn't hold for these examples. So one thing I should say why we consider this a superactivation is if the quantum capacity is 0, then also the catalytic quantum capacity is 0. That's maybe not obvious. The catalytic quantum capacity is your entanglement to be consumed, but then the net rate of communication is how many qubits you can get out minus the entanglement consumption rate. Okay, so what you can show is that if the quantum capacity is 0, the catalytic quantum capacity is also 0. Okay, so that's why I consider this a superactivation, because we can superactivate this catalytic quantum capacity. So that's all I have for now. The polar coding scheme is nice. What's known is the encoder, the decoder. The encoder is efficient. You can do it with O of n log n operations, sort of a butterfly-like Fourier transform, FFT type operation. You can decompose it that way. The decoder is a linear number of quantum hypothesis tests. We're still working on that. There has been progress. Joe and Renato and Frédéric Dupuis had this paper on the archive where they show that the decoder can be made efficient if the channel is powered. Okay. So maybe this would be useful in addressing some of Daniel Gottesman's questions from the previous talk. Okay. So this is the most important problem, to make this decoder efficient for general channels. And then the other one, of course, is figuring out which channels are the good ones. I mean, this would make the scheme totally explicit, right? So there's been progress in the classical information theory community on this problem using approximation algorithms to compute which channels are the good ones. And then we may want to extend this to other scenarios like compression or lossy data compression, et cetera. Okay, so thank you very much.
Questions?
In the classical case, to achieve good polarization, you need very long codes, like 2 to the 20. Is it the case in quantum case as well, I guess?
I would think so, yeah. Okay. Right, so that's another bad aspect of polar coding. It's very long, yeah.
In your scheme, you were using the E-bit or half of an E-bit when both channels were bad.
Right.
But it didn't show up in your diagram. So where is the other half of the E-bit?
Oh, I'm sorry. That was just sort of supposed to be a figurative diagram, but they're there. You could draw a different diagram where they're there. Sorry about that.
But where are they? Are they still sent?
Oh, well, they're shared between Alice and Bob beforehand, and you're assuming you know the indices of the channels that are good for or bad for amplitude and bad for phase. And
So the other half is already with
available
Bob?
for Bob. Yeah, that's needed to show it works, but there was some work in the classical world on these schemes for private communication over a classical wiretap channel, and when they evaluated in practice how many secret key bits were needed, they were able to show in some cases that they were not needed. Also for Joe Renes for Pauli channels, they were able to show numerically that they were not needed for certain Pauli channels in the class of all Pauli channels.
One last question.
You described the recursive construction of these induced channels. I was wondering, is it possible to say beforehand which one of these 2 to the n induced channels you're going to get for a fixed channel to begin with, right? You start with a fixed channel. You do the construction. Is it possible to say which ones are going to be the good ones, which ones are going to be the bad ones?
That's what we don't know. I believe for your channel, you can actually compute efficiently which ones will be the good ones and the bad ones. But in general, there was work, these approximation algorithms to address this question.
Well, the
I
related,
can punch it in the paper if you want it.
the related question is how quickly the effect actually kicks in. That relates to Alexei's question. Is it understood from the
It's understood. I think it's fairly. It's understood that the block has to be long, like he was saying, 2 to the 18 in practice.
Thanks.
Let's thank Mark again.